Hi, and I've been developing Scala for a couple of years in Arbor networks. And I work with Alexi, and one day Alexi sent me a message, with scripted message, with a puzzle. And this puzzle basically, for every letter corresponds a digit, and these numbers must add up, okay? So he sent me this puzzle where every letter corresponds one digit and two letters are different digits. And of course, there's another condition where the leading digit can't be 0. So I pick up my pen and paper and I start writing down, oh, you know what? These two numbers, like everybody would do, these two numbers, they can't make n bigger than 1 and n can't be 0, so it's 1. So I was very happy. I sent back a message, oh, Alexi, it's n equal 1. And you know what? Check this out. N is equal 8 and 9 because blah, and O must be 0. And he said, wait a minute. I was talking about doing programmatically. Okay, it makes sense. Basically, he was talking about, this is Ed Kemet, this is Bartosz. He was talking about a blog post, a series of blog posts made by Bartosz for C++ developers. Like, this is what he normally does. He writes great blog posts about functional programming techniques and FP like goodness for C++ developers. So he gives like C++ implementations. So he was basically talking about these 4 blog post series about, tonight I'm going to use the M word, okay? So only for tonight. So he was talking about how to solve that problem, that simple problem, using monads. And doing that, try to explain to C++ developer what actually monads are. We all know, or probably we know, all the benefits of monads, right? So we don't have to go to the benefits. And we can actually go straight into the first way to implement that problem. And that's the way he implemented. So basically, if we look at the search space, it's not that big. Okay, it's like 2 million possible way to like look for candidate solution. So, and then all we have to do is just prune the solutions and get the only solution that solved that little puzzle, okay? So let's start with the first implementation. We have the problem. Let's look how a C++ developer could implement this problem. Of course, in the old days, or even now, people is doing like nested for loops with mutable variables. Okay, I'm saying a lot of bad words now, but the point is, what we're doing in Scala is basically the same thing. We're generating a lot of substitutions, and then we are testing with some sort of constraints. We're checking the conditions until we find the solution. Okay, this is Scala code, pretty similar. Basically, it's doing almost the same thing. So if we follow this lead, we can actually do our first correct implementation. And we write something like this, where we have a list of digits here. And then we basically cycle through all the lists with our conditions until we actually find our solution. And then we prune with our, we check for all the candidates for the one that actually solved the problem here, okay? If you're new to Scala, there is a cool thing here. So as you can see, I'm filling the letters with a digit. And what I'm doing here in this list, I'm basically doing a kind of, basically it's a base 10 shift. So in other words, send will be the number where all the digits, all these letters, form, okay? I'm basically shifting. This is the first parameter and so on. So what we're doing here, we are pruning all the candidates until we find the solution. Okay, no surprises? Yeah, okay, the Bartosz in the blog post saying, oh, wait a minute, that's not very nice. And I have to be honest, when I did this slide, I made a mistake. Copy and paste, modify, I made a mistake, it's normal. So that's the past. Now let's talk about functional programming. But before doing that, we need to introduce Jimmy, okay? Who is Jimmy? Jimmy is a bingo caller, okay? He picks numbers until somebody screams bingo, okay? He chooses digits. This is what Jimmy does. So let's give Jimmy a jar with 10 numbers, okay? What he's doing is basically picking one of these numbers and saying S is associated with 0, and then has a leftover here, okay? All the remaining digits. Those are all the remaining digits, all these remaining numbers. So where I'm going now, I'm talking about Schrödinger, okay? So I need to bring Schrödinger into our conversation. Why I'm bringing Schrödinger here? Because until Jimmy look at the number, okay, he doesn't know what number is there. But as soon as you look at the number, with the multiverse concept, we can actually spawn 10 different universes, okay? We are spawning one universe for each number he can actually pick. And of course, we have the number and the leftover, okay? 10 different universes. So for instance, if you get into this universe, S correspond to 1, what's going to happen? We would like to associate E with another digit, and we spawn 9 worlds now, okay? Very easy. And then so on, 8 worlds, 7 worlds. We keep going with our life. And at the end, maybe we destroy the universe. It's very cheap with functional programming. So until we found the universe where actually all the constraints are satisfied. Now, we would like to implement this, okay? But how functional programmers do this? So how functional programmers basically deal with these state transitions and this way to keep state like going on, like how can we deal with all these universes without getting crazy and without using mutability? Of course, we can try, the first try will be the state monad. This is how the FP guys are dealing with state. Okay, where do we start? Okay, state monad. We need to think about the simplest way to define a state transition, okay? So if you want to like define a stateful computation that brings us from a state S to another state with a value, this is a possible implementation, okay? And we can call this state. Okay, bear with me. So this is like a simple implementation of the state monad. And if you look at the companion object, that function is in here. So in other words, we are able to create this state passing the function that define my stateful computation from an initial state to the next state with a value. This is the way we could do to wrap a function that basically define a stateful computation. Okay? So instead of having a type as a function, we are having this object wrapping this function. Okay. If you're good, and actually ScalaSyd already done this for us, we should implement map and flat map right. We don't go down that path tonight. So we assume that map and flat map are correctly implemented. And I would like to show you this little method here, eval. Basically, when we have a stateful computation, all we have to do is basically give the initial state, and what we get back when we want to evaluate is just take the A out. So basically, if you run with this function, we just take the result right. That's more or less in 5 seconds, the state monad. But if you don't have this book, you should buy it. It's FP in Scala. I don't get any money for this, so it's like, and there's a chapter just for the state monad. But if you're new to this, it's very tough, like at the first try. So just concentrate on the function. Everything, the key point is here. Now let's keep going. So as I said, we need a function. The function that pick a number and gives us the leftover. Okay? Let's call this function select. From a list of possible numbers, we pick a number, head, the first one, the first one on the head of the list, and we return the tail. Okay? It's a legit function to do what we need to do. Okay? Now, let's run this function. Let's see how it works. Okay? So we pass the function to state. We bind these two stateful computation together. We bind them with flat map. Okay? And we get the value of the first state and the value of the second state into B, and then we map here. Now, quick question. What is the type of S? What is the type of this form comprehension? Okay, we have to look at the monad. must be a state, and that's easy, okay? It's a state. But what is the type of S and the type of A? The type, as we said earlier on, is the list, okay? The type is the list of integer. And the A, the value, because we are mapping here the value, it's a map, okay? It's association, okay? Now, if you're new to state monad, that freaks you out. The fact that, what is the result of S? What's the value? There's no value. This is a stateful computation. The only way you have to use this thing is to evaluate something, to run something, okay? And we're gonna run a list with these two integers, where 1 will get associated with A, and 2, the second peak, get associated with B. And between these two guys, the flat map is passing the list without the number, okay? That's a way to use the state monad here. And of course, this is what we're expecting. Now, let's change the numbers, okay? Nothing new. So, with the state monad, we are passing the state. If we add C, that is the expected result. By the way, I'm going to use this symbol from now on because I don't have enough space. And basically, it's a ScalaSyd shorthand for a list. So it's basically a list. And if you look at maybe something like this, it's some Scala collection range crap that if you try to use it, inside, I should have done this, yeah. You try to evaluate inside of your thing, it says, oh, no, I want a list. I don't want that range thing. So, of course, okay? So it works. So basically, from now on, we're going to use this symbol as a shorthand. Let's keep going. So, no surprises here. With a list from 1 to 4, we get this map. But what we're getting, let's think about Jimmy. What we're getting is a single multiverse. So we are going that first into the universe creation, all the multiple universe. We're going that first until we get only one history. So we are not branching, okay, this multiverse. So it's a single multiverse. So what we want, we would like to branch out. We would like to, I don't know, do something like, list is very good to do the cross product, okay? So if you look at the full comprehension of list, we know how it works. It's easier to even understand than the state monad, okay? It's going to do the cross product. So we know the result. We have all the different combination. We would like something like that, but with this result, okay? But without using that function, you know, to filter out the candidate that we don't like. So in other words, we should fight to merge these two monads together until the end. We would like to mash these two monads together in order to get a monad that actually behaved with these two orthogonal properties of these two monads, the list monad and the state monad. So in other words, we would like to use what they call monad transformer. So state T with list, we are basically mashing those two monads together. So if you look at the ScalaSyd library, not for every monad, that's not true. For some monads, you can have a monad transformer. For instance, there is no list transformers known for ScalaSyd. I'm not saying it's not possible, I'm saying there's no known list T. But anyway, long story short, we're going to try this out. Why? Because it's very powerful. Because we get the power of both monads, but it's also scary. It is scary. When you have a hybrid, it is scary. Let's see how much scary. Do you remember the select a few slides ago? We go from this state to this state, and we have this value. That was very clear. We pick a number. How does it work with the state T? This is state T, okay? It's one step further. State T doesn't give you back this tuple. It gives you back that tuple in this context, F. And in our case, the context is list. This is where we are actually merging those two monads. We are mashing them together, okay? So the result of this next state and the value is in a context, and in our case is the list context. This is one of the implementation. It's the simplest implementation I could come up with. What it does is very simple. If you give me like a list of numbers, for every number, I'm giving you all the possible options, picking up one number. So for every number, I'm bringing you back the number and the list of the leftovers. Okay, this list is just filtering out the number they pick. Super easy. So doing this way, we're gonna have this list has the same number of elements of this list, but here we have the number picked and the leftovers. With this function, we are basically doing this, okay? We have 10 digits, we are creating a list of universes, okay? That's exactly what we're looking for. That's the function we're looking for. Let's run it, okay? Let's run it with the same code we use for the normal state, okay? So, what are we expecting here? If you ask for the lows, you pass your type and you check. And because list is a monad plus, then also our state L is a monad plus. So, before rolling out our solution, the final solution, I would like to just introduce also prevent. Is exactly the same thing as guard, but it's going to negate this condition. Okay, so here we have the only solution where A is not bigger than B, greater than B, and A plus B is equal C. Okay, that's the last Lego brick that we need before rolling out the final implementation. Okay, so this implementation, I translated this implementation from the Bartosz Haskell code directly into Scala code. So, as we saw earlier on, the solutions we evaluate with all the digits, and we pick the first solution and we print it out. Okay? And our tape is here. No surprises. Now, the select is the select we did together earlier on, and then we have this go function. Let's have a look here how we call this go function. So, the go function has a list of characters and a map with all the substitution, okay? The way we're going to use this go, it is actually a recursive function, we're going to start with a list full of characters, all the possible characters, and an empty map. What we want, if we look at the type, what we want is a function that basically empty this list and build the map with all the possible character digits. And of course, we want to prune and get the real result. So let's have a look at Go very quickly. So Go, there are two conditions in this pattern match. The second one is the one that actually recur, and we are extracting a C, and what we do, basically we are adding that C with a digit into the map, and we are calling Go with the leftover, the tail of the list we pass to it. It's kind of hard code. If you're new to ScalaSyd and functional programming in Scala, it's very hard, especially because I'm using this bind symbol. This bind symbol is basically flat map. So what I'm doing here, I'm basically, as I said, emptying this list, creating this map in a recursive fashion. This is the solution that Bartosz proposed. And after that, when I'm at the last element, I'm adding the last element to the map, and then I'm calling prune. Okay? So far, all we've done is creating this map with all the association character digit. And this is the final solution, and that's it. We're going to prune it. We saw prevent, we saw guard, and this is pretty readable. And the way we are creating the send number is basically we're mapping all the char to the map, and we basically get out the number, and then we reduce as we did earlier on, and we create the numbers, and we're done. And we return the numbers. Send more and money. Why I did this talk? Because as soon as I saw this implementation, I thought, oh, wait a minute, we can do exactly the same in Scala, exactly the same. So if you look, it's creepy how similar it is with our implementation. And I think it's true when Martin Odeski said, that Scala is actually the gateway drug to Haskell. It's completely true, because make you appreciate and make you actually, at least for me, help me study more and learn more and more about the Haskell. So yeah, I'm gonna leave you the slides if you wanna look how similar these two pieces of code are with Haskell. Yeah, even this one, look at here, it's exactly the same. Okay, so just before closing it, I'd like to say that I had so many other things to say about this problem, and especially I would like to show, not today, maybe another time, probably at FPSeed, a way to actually have a cleaner code without that Go recursive function, using perhaps traverse sequencing, and also parallel execution using applicative instead of monad. So it's a totally different talk, but it's very interesting because I also came up with a different algorithm working with the modulo of the number. Anyway, and also I found a paper about parallel genetic algorithm to solve these kind of problems that is blazing fast. And it's very, very interesting. So this is all material for FPC talk. And of course, we can solve it at compile time with shapeless. At compile time, you get a solution when you compile it. And in the references, we can talk over a beer anytime about it. And the references, I give you all the link about all the things you can find funny. Anyway, I hope you found one or two interesting things, and I thank you for your attention.
Thank you. Has anyone got any questions?
Oh my God. It's easy, okay, thanks.
No, I'm just curious. How does that solution act when you've got a problem, like say it wasn't send more money, say it was just more, or something, a problem which there is no valid solution?
Oh yeah, it's a good question actually. So if you go to the final solution, this one. So basically here, it's going to explode because I use head. Oh, actually no, it's going to explode.
You need
safety. But anyway, so when you eval, that's actually a list of all the solutions. So that will be an empty list. But that's a good question, because every time, let's say this is not a state T or it's just a list. These guys are giving you back an empty list. And we know from comprehension with an empty list what it does. It does nothing. It gives you back an empty list, no matter how big the lists in the for comprehension are. And this is what guard does. Nothing else but the empty list. One thing I didn't say is that this is not if, like, you know, the if in Scala is like it's a macro thing that rely on basically nothing. It's like dynamic language, okay? It's expecting you to implement with filter or filter, and if you don't have it, explodes at runtime. This is not happening here because this is actually, this guy here has a flat map. So it's actually a compile time you can do it. So when we don't have a solution, this guy returns nothing, and we yield an empty list.
So if I understand it correctly, does it iterate the whole search space?
Yes. No, it actually depends when you say the whole search space. That's a good question, because wait a minute. I'm going backwards. Yeah. So you're not picking up like 0 and 0. No, you don't. Yes. So you're pruning that part of the space, but we're not doing any smart pruning like forward pruning. No. We're just all you know is that the map coming out from there, okay, from that go. So when you're here, you know two things for sure: that every number is different of the character. You know this, and the other thing you know, I forgot about it. No, I don't remember. The other thing you know is that you have every character. This is all you know. But yes, so up to there, you explore only those with those conditions. Yeah.
Yeah. Thank you very much.
Thanks.